So kinematics. Basically just the study of how position, velocity, and acceleration are related to each other. And do you have any equations relating those together so far? How do those quantities relate to each other? For example, how do we define those in the first place? Like, what is velocity? What is acceleration? Yeah, velocity is just the derivative of position, and acceleration is the derivative of velocity. And for now, I'm going to use x for position. But we could use y for position instead, or more generally, we might use r for position. In fact, for now, let's use r for position. R in the sense of radius. So let's use r for position, and we can replace it with x or y later on if we're looking at just the x component or just the y component. So we know that by definition, velocity is derivative of position. Velocity is how fast your position is changing as time passes. And likewise, acceleration is describing how fast the velocity is changing as time passes. And formally, these should be vectors. But what we're going to be doing here in terms of the equation applies not only to the vectors, but also to their individual components. So just the x components, just the y components on their own. And the whole idea of kinematics is largely based on what happens if the acceleration is constant. Because acceleration is caused by a force. Specifically, the net force on the object equals mass times acceleration. So that means if you know the total force, then you can figure out what the acceleration is. So acceleration is often where we start, because maybe you know something about the force acting on the object. And let's assume the force is constant. Everything we're going to be doing with kinematics starts with the assumption that the force does not change. Because if the force is constant, if the force does not change as time passes, what does that tell you about the acceleration? If the force is constant, then yeah, the acceleration also has to be constant. Because mass is constant in general. The mass of the object we're expecting does not change. So the only way the acceleration could change is if the force also changes. If we're assuming we have a force that doesn't change, that means we have an acceleration that also doesn't change. Acceleration is going to be constant. And that makes this a lot more predictable, because if we know the acceleration is constant, we can figure out what the velocity has to be. And if we know what the velocity is, we can figure out what the position has to be also. What would be some examples of this? What would be some real world situations where the force is constant on an object? What's an example of a force that doesn't change as time passes? What's an example of a force that is constant, a force that doesn't change as time passes? Or an example of an object experiencing a constant acceleration as time passes? Yeah, if you've got just a ball falling to the ground, even if it's currently on its way up, like let's say you just throw something, you throw it, and while it's in flight, what's the only force acting on it? Yeah, you've got a gravitational force. And the force of gravity on that object is a downward force equal to the mass of the object times the acceleration of gravity. Mass is constant, acceleration as gravity is constant as long as you're not moving much further or much closer to the planet. So that means that the force of gravity is constant. And the force of gravity is therefore going to provide a constant acceleration, which makes the velocity and position very predictable. So of an object in free fall, which doesn't necessarily mean it's on its way down, the entire flight path counts as free fall. Free fall just means the only force acting on this object is gravity. So that would be an example, a very common example of an object with constant acceleration. Another example might be if there's some other force on it that doesn't change as time passes. Like for instance, the engine of a car. If you're talking about a car starting up and getting faster and faster, for at least a short period of time, we can treat the acceleration as constant. The engine is causing the car to accelerate. And of course, that's not going to last forever. After a few seconds, other forces become pretty important. Like you get a lot of wind resistance, and the engine can only go so fast anyway. But for a short period of time, a car getting faster and faster on a road is going to count as almost constant acceleration. So we can use these same principles. Or a rocket with its engine turned on. As the rocket's engine pushes it forward, the engine's providing a constant force. In that case, the mass of the rocket is actually going to be changing because it's losing fuel. But for a short period of time, the mass doesn't change very much. The force of the engine is constant, so the rocket's acceleration will be almost constant for at least a short period of time. So the equations we're going to be developing here apply in any of those situations. Any situation where the acceleration is constant, or at least a short period of time when the acceleration is almost constant, if there's very little change in the acceleration. Any questions on that so far? So let's explore the results of this. We're assuming constant acceleration. That's really the foundation of everything we're going to be doing. We're assuming constant acceleration. And if you know the acceleration, how would you find the velocity? How would you get rid of this derivative here? Or what's the opposite of taking a derivative? Yeah, you take the integral. If acceleration is defined as the derivative of velocity, then that means velocity is going to be the integral of acceleration. And integral of acceleration. If acceleration was a function of time, we'd have to know what that function is. If the acceleration is changing, we'd have to know what that function of time is, and we'd have to integrate that function. But we're assuming acceleration is constant, which makes the mathematics here much easier. What's the integral of a constant? Like, for instance, if you were just integrating 5 dt, what would the result be? Yeah, that constant times, well, you could pull the integral, or pull the constant out of the integral and get integral dt. And what's integral dt? Yeah, that's just t. Because again, this literally just means summation of tiny bits of time. If you add together all the tiny bits of time, you get the time. So this just becomes acceleration times time. And since this is an indefinite integral, we also have plus a constant. But do you know what that constant would represent? If velocity equals acceleration times time plus a constant, how would you figure out what that constant is? Ideally, this equation should work for any value of time, right? So we should be able to plug in any value of time. What would be the easiest value of t to use here? Yeah, if we just plug in 0 for time, at time 0, we get velocity equals acceleration times 0. Acceleration times 0 is just 0. So this constant is the velocity, specifically the velocity at time 0. Usually it's called v sub 0, or you might call that v sub I for the initial velocity. So all this is really saying is the velocity after some time has passed is the starting velocity plus the acceleration times how much time has passed. In fact, if you look at this in terms of the units, what is acceleration typically measured in? What are the units of measurement for acceleration? Yeah, meters per second squared. And then time is measured in seconds. Multiply those, and one of the seconds cancels out, so you get meters per second. Acceleration times time is a velocity, or rather a change in velocity. Acceleration is how much your velocity changes as time passes. Multiplied by time, time and time cancel out, so you just get the change in velocity. So acceleration times time is literally just the change in velocity. All this equation is really saying is your final velocity is your initial velocity plus the change in velocity. V final equals V initial plus delta V. That's really all this is saying. You've got your starting velocity, you add how much your velocity changes because of the acceleration, and you get your final velocity. But this means that as long as you know the acceleration, and you know the starting velocity, and you know how much time has passed, you can predict the velocity at any time later in the future. Assuming, of course, that the acceleration is constant. Or this also works in reverse. If you know the velocity, the final velocity now, and you know the acceleration that it's been going at, you can predict you can, I guess not so much predict, but you can backtrack and figure out what was the velocity some amount of time in the past. Or maybe you know the starting velocity and you know the ending velocity and how much time it took. You can now solve for the acceleration, figure out how much it was accelerating during that period of time. 4 unknowns. If you know any 3 of them, you can immediately solve for the 4th. Any questions on that so far? So this is one example of a kinematic equation, in the sense of an equation that's always going to be true as long as the acceleration is constant. And kinematic just means having to do with motion, literally. But we typically use it to mean the sorts of results we get if the acceleration is constant. And this can be split up into components also. You can say that the x component, this works for the x component, so you could say the final x component equals the x component of acceleration times time plus the initial x component. And separately, you can say that the final y component of velocity is the y component of acceleration times time plus the y component of the initial velocity. So these are both valid. If you look at just one component at a time, the equation is still true. Any questions on that so far? So we have a formula for velocity at any time. Let's take this one step further, because we also know velocity is the derivative of position. So we can undo that derivative with another integral. If we apply the integral again, we know position is the derivative of velocity. Therefore, sorry, other way around. Velocity is the derivative of position. So we can find the position at any time by integrating the velocity. Position should be the integral of the velocity. And we know the velocity can be found by this formula. So if we fill that in, position is the integral of acceleration times time plus starting velocity. With respect to time. So if we can integrate this expression, we'll have a formula for position at any time. And how would we integrate that? If we split this up, what's the integral of AT? Yeah, AT squared. And also with it divided by 2, because t squared would become 2t when you take the derivative. But we don't want 2t, we just want t. So we need an extra divided by 2, so those cancel out. So AT is going to become a t squared over 2. And then v naught is a constant, and like we saw earlier, the integral of a constant is just that constant times time. So we get that constant starting velocity times time. And also, again, it's an indefinite integral, so we're going to have plus another constant. And what would you expect that constant to represent? Yeah, the initial position. Again, because you could plug in 0 for t, that means these will both be 0. So this constant is the position at time 0. So initial position, r sub 0. So that would be an equation we can use for the position at any time. As long as you know the acceleration, the starting speed, and the starting position, you can predict where the object is as a position vector at any point in time in the future. Or the past. You could even use a negative value for t to backtrack where it was in the past. And again, if you take a look at the units here, acceleration is still meters per second squared. But we're now multiplying by time squared. So we're multiplying by seconds squared. So second squared and second squared cancel out, and we get meters. Likewise for this term, velocity meters per second, multiplied by seconds from time. And again, seconds cancel out, we're left with meters. And of course, position itself is measured in meters. So these are all measures of distance. We've got where you start plus how far you travel because of your starting speed, plus how much extra you travel because you're accelerating. So each one of these terms represents a change in position. You could think of this as how far you would be traveling just because of your starting velocity if you weren't accelerating, if you were staying that speed the whole time. So this is how fast you would, or how far you would travel if you were just moving at a constant speed. But this is how much extra you travel because you're accelerating. So this is still initial position plus change in position equals final position. It's just that the change in position is caused by the combination of how fast you're traveling to start with and how much you're speeding up. Any questions on that kinematic equation so far for predicting the position at any time? And also, just like the velocity one, this could be split into components. You could look at this as just the x components. And the x component of position, we usually just call x anyway. So the x value, the horizontal position, equals the x component of acceleration times time squared over 2, plus the x component of the initial velocity times time, plus the x component of the initial position, usually just written as x sub 0. So this is valid for x, and also we could write it out for y. We could say the y value, the vertical position, the y component of position, equals y component of acceleration times time squared over 2, plus y component of starting velocity times time, plus starting height. So we can split this up into components to get two equations, one relating horizontal position and time, the other relating vertical position and time. How far it has moved forward from the starting point, how far it has moved up and down from the starting point. Any questions on that so far? All right, then let's try out some examples now that we've got these formulas. I'm going to put these up at the top of the board for reference. And let's start with, let's say, a car. Let's say you've got a car that's on a straight line racetrack. And let's say this racetrack is 1,000 meters long. Well, it's a little too long. Let's say it's only 500 meters long, half a kilometer. So we've got a 500-meter racetrack. And let's say this car starts off at a complete stop. And let's say at time 0, it hits the engines and starts moving. And let's say it can accelerate at, if you just completely floor it, Let's say its acceleration is 5 meters per second squared. And we could figure out, what's one thing we might be able to figure out here? What information could we find in a case like this? We could figure out the final velocity, except there's one slight problem there. We know the initial velocity. If we just list out what we know the acceleration is 5 meters per second squared. We know the initial velocity. What would be the initial velocity here? If it just starts from rest, the initial velocity is, 0. Also, since this is a one-dimensional problem, we don't really need to call these vectors. We can just treat the position, velocity, acceleration as just the x component anyway. So I'm going to ignore the vector signs here because this is a one-dimensional problem. We've got a starting velocity, we've got an acceleration. We don't know the final velocity. That is the velocity when it crosses the finish line. We could use this equation, but the problem is we know the acceleration, we know the starting velocity, but we don't know the final velocity and we don't know what time it crosses the finish line. So we can't really use that equation yet. We've got too much unknown. We don't know the time it crosses the finish line. But how could we figure out what time it crosses the finish line? Yeah, if we use this equation involving position versus time, because we know the final position, let's say x initial, it starts off at 0 meters. And you can basically define 0 meters as wherever you want. You can choose any location to call the origin of the coordinate system. So let's say we call this location x equals 0, and then the other end of the track, x equals 500. So x0 would be 0 meters. X final would be 500 meters. Because we know where it starts and where it ends. And of course, it's not coming to a stop here. It's going to be blasting through the finish line at some high speed. But that's the end of the track, so that's what we care about. So let's see if we can apply all this to this equation. And I'm going to write this in terms of just x components. We've got x final equals acceleration times time squared over 2 plus initial velocity times time plus initial position. And the acceleration and initial velocity should be thought of as x components because we only have an x component anyway. So if we fill in what we know final value is 500. And that's 500 meters, but since everything here is in meters and seconds, I'm going to leave off the units. We know we're going to end up with time being seconds anyway. Acceleration, 5 meters per second squared, times time squared. We don't know what time it crosses the finish line, so we'll leave that as an unknown variable. Initial velocity, we know is 0. Starting position, we also know is 0. So we're left with just 500 equals 5 halves t squared. And now that means t is the only unknown. So how could we solve that for t here? How would you isolate t in this equation? Yeah, divide both sides by 5 halves, which is really the same as multiplying both sides by 2/5. 2/5 of 500 would be 200. 5 halves and 2/5 cancel out, so we get t squared. And then what? Right, take the square root. T is square root of 200. And we can split that up into 10 times the square root of 2. So 10 times the square root of 2, which is going to be about 14.14 seconds. So that means it's going to take, if this car is accelerating constantly the whole time, then the time it takes to reach the finish line will be 14.14 seconds, 10 times the square root of 2. Any questions on that so far? And now that we know what time it reaches the finish line, what else can we now calculate? That time that reaches the finish line was a missing piece of information from earlier. Remember, if we go back to this equation, we knew the acceleration, we knew the starting velocity, we didn't have time, but we now do have time. We know what time it reaches the finish line. So if we plug all that in, we can now calculate, what does this represent? That final V represents the speed it's going at where? Yeah, at the 500 meter mark. We can now figure out how fast it's going as it blasts through the finish line. So let's try that. We can write out the velocity equation. Velocity, I'm going to call this velocity final equals acceleration times time plus velocity initial. We know the acceleration was 5 meters per second squared. Again, everything's in meters per second, so I'm not going to worry about the units for now. Time we now know is 14.14 seconds. That's the time it crosses the finish line. Plus starting velocity was 0. So 5 times 14.14 would be 70.7 meters per second. So if the car is able to maintain this constant acceleration the whole time, then it will cross the finish line 14 and a little bit more seconds later at a speed of about 71 meters per second, which is something like 150 miles per hour, if I remember correctly. So realistically, it probably wouldn't be able to maintain that acceleration the whole time. Once it gets going that fast, or even close to that fast, air resistance is going to be a significant force, and it probably wouldn't be able to maintain this acceleration. But if it could, then this is what would happen. Any other questions on that? There's one other very convenient variation. Actually, one more thing I want to mention about this. This equation involved a t squared. In this case, we were able to just manipulate some terms and take a square root, and that was it. But that's because these terms both happen to be 0. If these terms weren't 0, if you had like a number equals something t squared plus something t plus something, you couldn't just isolate t the usual way. What would you have to use instead? If you've got something t squared plus something t plus something, how would you solve an equation like that? Yeah, you need to use the quadratic formula. Alternatively, it might be possible that it's factorable, but that's not very likely. If it's factorable, go ahead and factor it. But if it's not factorable, or if you don't notice any immediate ways to factor it, then you can use the quadratic formula. Rearrange the equation so you just get the whole quadratic on one side and 0 on the other. So something t squared plus something t plus something equals 0. And then apply the quadratic formula. You will end up likely with 2 solutions, probably one positive, one negative. So use whichever one makes the most sense. Like in this case, we should expect the car to cross the finish line after it starts. So you should expect a positive value for t. A negative value for t wouldn't make any sense there. Any other questions on these equations so far? And notice that in order to find the final speed, we had to find the time it crosses the finish line first. But there's actually a way to shortcut around that. It's possible to find the final speed without figuring out the time first. And one way to do that is to set up an equation using substitution. We have final speed equals acceleration times time plus starting speed. We're just going to call this V initial for now. And what else do we know? We also know that the final position, I'm just going to use X for position here. Let's assume it's a one-dimensional system. Final position equals half the acceleration times time squared plus initial speed plus initial position. So we could make some substitutions here. The main problem here is time shows up, and it'd be nice to be able to deal with this without having to worry about time. It'd be useful if we could figure out how fast the car is going 500 meters further down the road without having to know what time that happens. We can do that by creating a new equation that doesn't have time in it at all. And one way to do that is to isolate time in one equation. For instance, if you isolate t here, what would you get? Can you solve that for time? Yeah, V final. Well, we have to subtract V initial from both sides first. And then afterwards divide by A because of order of operations. In other words, delta V divided by acceleration. So that would tell us the time. The amount of time it takes to accelerate a certain amount is delta V divided by the acceleration. If we substitute that in everywhere we see time here, we've got times there. If we replace every t with this, then we should be able to get a formula that doesn't involve t at all. So let's try that. X final equals acceleration over 2 times delta V over acceleration squared. Plus V initial times delta V over acceleration plus X initial. And now we can simplify this a bit. We have X final. Also, I'm going to go ahead and subtract X initial from both sides just to keep things a little easier. Because what do we call X final minus X initial? Yeah, that's just delta X. Now we don't need to worry about where it starts and where it ends. All we need to know is how far it travels. In this case, that's just 500 meters. So we've got acceleration over 2 times delta V squared divided by A squared. And what's immediately going to happen with those A's? Yeah, one of those cancels out. We've still got a single A in the denominator. And then plus V initial times delta V divided by A. And we subtracted X initial, so that's gone. Also, to get a common denominator here, I'm going to try multiplying this by 2 over 2. That way it's the same denominator. So we get delta X equals delta V squared. And I'm going to go ahead and write this out as V final minus V initial. V final minus V initial squared plus 2 times V initial times delta V. And if we write that out as final minus initial, we've got 2 times v initial times v final plus, or no, minus, I should say, because we're subtracting v final minus v initial, minus 2 times v initial squared, all divided by 2a. And at this point, this is pretty messy. But we can simplify this quite a bit, I think. If we, to start with, let's try multiplying both sides by 2a to clear the fraction. Let me put this up here. So multiplying both sides by 2a, we get 2a times delta x. On the other side, we're left with all this. V final minus V initial squared plus 2 times V initial times V final minus 2 times V initial squared. Again, a huge mess. So let's see if we can simplify it. If we actually multiply this out, we'll get V final squared minus V initial times V final twice plus V initial squared and then we also have all this plus 2 V initial V final minus 2 V initial squared. But when we simplify that, what's going to happen? Does anything cancel out here? Yeah, we've got a plus 2 V initial V final and a minus 2 V initial V final. So those are going to cancel out. We've also got V initial squared minus 2 V initial squared. So we end up with V final squared. One of these cancels out, we're left with just minus V initial squared. So we get 2a times delta x equals V final squared minus V initial squared. And since that's the final value of a velocity squared minus the initial value of velocity squared, we could write that as delta V squared. So 2 times acceleration times delta x equals delta velocity squared. And this is a very useful equation because it relates the velocities. In fact, it might be easier to just leave it in this format. Or add V initial squared to both sides. This might be the most convenient form to write this equation, because this now allows us to write out the final velocity if we know the initial velocity, the acceleration, and the distance traveled. And time no longer shows up in this equation at all. We got rid of time by making this substitution. So what's left is a time-independent equation. And this is another of the kinematic equations. This is true as long as the acceleration does not change. But this allows you to find the final velocity in terms of the initial velocity, the acceleration, and the distance traveled without having to know how much time it takes. So you could just plug in those values. The starting for the race car, for instance, the starting speed was 0, the acceleration was 5 meters per second squared, and the distance to the track was 500 meters. So if you just multiply 2 times 5 meters per second squared times 500 meters plus 0, and then take the square root, that'll tell you the final speed without having to know what time it is. So this can be a very useful shortcut. I'm not going through the whole process of finding it all at once, of course, but just from this formula as a starting point, you can use this to figure out the relationship between the initial and final speeds versus the acceleration and distance traveled without having to know how much time it passes. And that is often a useful shortcut because it allows you to completely bypass the extra steps of figuring out how much time it takes. Of course, if you want to know what time it is anyway, then you may as well find that first using these equations. But if you don't care about time and you don't know what time it is and you just want to know how fast is it going after a certain distance, this is a very useful formula to use. Any other questions on that? All right, try that out on some examples on your own just to get some practice with it, and I will see you next time. You're welcome.